Today we are going to cover a very important topic called bias and variance trade-off. So actually in the whole homework too, it's all those plots we require you to draw. It's about bias and variance trade-off. So the homework itself gives you a very intuitive practice about what's truly how do you select models and why do you select models. The reason behind is bias and variance trade-off. So today's section we are in actually just about learning theorems. It's not about a specific algorithm. But we are still inside the classification section. And so the reason why I start to talk about bias and variance trade-off is K-nearest neighbor is an extremely good algorithm to explain because it has certain properties that makes you think about why do you even need to pick or select models. So last class, I talked about scalability of K-nearest neighbor. So I had quite some new slides, extra slides as to read contents in lecture 9. And it's about why KD tree, how the KD tree helps you to improve K-nearest neighbor scalability. So if you are interested about how to use KD tree and why KD tree can help the search in K-nearest neighbor, so please feel free to check them out. And also in the extra lecture of lecture 9, so I put K-nearest neighbor is actually a very good classifier. So you can prove if the Bayes error, so I'm going to cover a little bit about Bayes error as epsilon, and K-nearest neighbor, when you have infinite number of training samples, K-nearest neighbor guaranteed the generalization error is 2 epsilon. So it's a bounded, if you have this irreducible error as epsilon, the optimal K-nearest neighbor when you have infinite number of training samples is 2 epsilon, bounded by 2 epsilon. So it's a very good predictor, both for regression and also classification. But what I said, I mean, I'm pretty sure a lot of you don't even understand a lot of those terminologies. But if you are much more advanced than the basic level we try to cover, please read those extra lectures. And actually, I know quite a few of you already doing machine learning research, pretty advanced version. So please feel free to check out those videos. So, all right, let's talk about bias and variance trade-off. So the figure reminds us or like kind of encourage us to think about bias variance trade-off is really this figure. So when you facing this type of data, the training data, what should be the decision boundaries? So this problem we are trying to learn to distinguish the orange versus the blue. So maybe people in the back seat can read the color very clearly. So there are 2 different kinds of samples in this 2-dimensional space. And the color represents the class 1, the orange color is class 1, blue color is the class 2. If you use a linear boundary, and this is the orange region, and this is the blue region, you can tell there are quite some errors you make, even for actually on the training data. And this is a K-nearest neighbor-based classifier, and the K equals to 15, which is a pretty large number. So you can also vary the K, to reduce it to even just 1. When you only consider one nearest neighbor, in K-nearest neighbor method, actually you don't train anything, but you still can learn the training error, right? So this essentially k near k equals to 1 segments the regions into something called Variance diagram, or it's just whatever centered around this each training samples. I'm enforcing a certain label constraint. And essentially your training data segment the two-dimensional space into all the smaller subspace. And each subspace follow the labels defined by that training sample. So this case, you can tell this is a very bizarre segmentation if you think about it, because whatever, if there's a small changes in the training data, and the segmentation will vary a lot. So, but this has, the k equals to 1 has no error at all on the training loss. If you just, because, yeah, it has no error. In the end, it's almost equivalent to k nearest neighbor 1k equals to 1, minimize the training error to 0. So everything we covered before, we normally have a representation of f, we have a scoring function to look for the f, and we're always trying to minimize the scoring function. And if we think about it, is that goal the right goal? If we think about this situation, because if our goal is just to minimize the training error, and this is the best classifier, best ever, because it has training error 0. But in fact, just roughly you can think about this is clearly a better classifier, even though it has certain errors here. So what is this? And why minimizing training error equals to 0 goes to 0 is bad? What influenced our decision? So that's the reason is we want to, because our final goal is to generalize to the future data. So what differ these two cases is something called bias of the estimator, and this is a very low bias estimator. This has a medium bias, this has this is high bias, this is medium bias, and this is high bias. So that's roughly the concept of biases, which roughly is, so I have there's some kind of true models behind my data. Good bias or low bias means my model is very close to the true model. Okay, so the figure also tells you about something called variance. Variance means when you varies the training data, I could have some kind of differences, maybe you sample differently, because in the end, your training data is a sample of underlying distribution, right? You get all in part. I mean, you normally don't get all the possible data. And if that's training data is a subset, of course, then there's a lot of randomness there. And there will be differences across different variation of training data, and how is your model reacting to the small variation of the training data. For example, for this case, if your training data varies, the segmentation will change a lot. That means this type of model varies a lot. And formally we call this has high variance. But for this type of formulation, even if, assuming I remove some of the data there, so if in my random sample, so assuming in this case, if I change, this data is not selected, there's another orange data here or maybe there, and then my segmentation will look really different, right? My orange section, we will add some new section orange because just that two different training data. However, in the linear model case, if I don't select this data, will my boundaries change at all? It's highly likely that boundary is going to shift very, very little. So if I remove or maybe random sample, add some other orange data here, and it will not change my decision boundary much at all too. So this is what I mean, it varies very little with the randomness of the training data. So this type of model, we call them low variance model. Questions? It's just an intuitive explanation, and later we are having the equations. But before the equation, I want you to have an intuitive understanding about what those equations are trying to capture. All right, so this is the classification, low variance model, high variance model, high bias model, and low bias model. So previously in the regression, when we covered the regression, we observed something very, very similar. So when we are given this multiple training data, so in this case, this is X, and the Y is the vertical direction, and don't confuse by this versus here. So this vertical is the Y dimension, and in this figure, color of the circle means the Y. And this is X1, this is X2, this is X1. So yeah, don't get confused. So this is X1, this is X2, and Y is that orange versus blue. And this is a two-dimensional classification, and this is a one-dimensional regression, and y-axis, it's the vertical axis. So this model is extremely precise on training data. The training error is 0, so you make no mistakes at all from the model you learned. And this has slightly training errors, and this has huge training errors. So very similar to the k-nearest neighbor equals to 1, and this model got the best training error. But is this a good model? So we actually did cross-validation before just to show you, and what we cared is the future performance. We use cross-validation error as a proxy as the generalization loss. So similarly, training error equals to 0. What the lesson we learned in both k-nearest neighbor equals to 1, also that piecewise regression curves, is the minimizing the training error is not always good. And then what do you use, right? Because we always, in the previous nutshell, the nutshell representations is we minimize the training error to look for the best parameter. However, these two cases clearly tells us, no, that's not good if you're just minimizing the training error. Okay, so now let's do bias and variance decomposition. Before I go to bias and variance decomposition, because we have to conceive, there's some kind of probabilistic knowledge I have to use, and I hope you still remember for example, the first. So we use capital unbolded letter to represent random variables, in this case maybe x. So in our setting, in fact, we have x vector, x1, x2, and xp. They are all random variables, right? And then together they are a random vector. And our output y is also a random variable. And actually the prediction fx, so now let's do that x vector. So I'm doing x equals 2, it's the vector. The fx is also a random variable. Because x is a random vector, there's a lot of randomness. There's a distribution behind. Fx is also a random variable. If the fx is related using the theta parameters, maybe in our regression case, you do fx equals to w transpose, like theta transpose x. Actually, theta is also a random variable. You can also think about theta as a random variable. All right, so yeah, they can all be considered as random variable. Now let's go on. So there's basic concept of a random variable is what? The mean of the random variable. How do you calculate mean of a random variable? So I hope you still remember from your maybe statistic 1 class. So random variable is, so you know assuming this is a discrete random variable, and to calculate its expectation is really just each possible values, because it's a discrete random variable, right? There are fixed number, finite number of possible values. Each value times its probability. And this summation over all the possible values is its mean. We also call it mean or expectation of the random variable. If this is a continuous random variable, what you do is not just summation over all the possible values. You do an integral over the probability density function, which is the px represented here. And this is the mass function, and this is the density function. So let me do a simplest example is assuming I have a Bernoulli variable. I hope you still remember what is Bernoulli variable. The Bernoulli variable, there's only two outcomes for this. It's a discrete random variable, there are only two possibility values. Assuming this random variable, let me just use maybe t to represent it. It has only possible value 0 or 1. And p t equal to 0 is 0.4. P t equals to 1 is 0.6. Then what is the expectation of t? So assuming you're doing a head and tail, then the chance of head is 0. The chance of head, I counted, you gain 0 if you got a head. If you got a tail, you gain 1. And the probability you flip to get the head is 0.4. Probability you flip to get a tail is 0.6. Then what's the average gain, what you could get by flipping many times? So if you have head, you got 0 return. If you got a tail, you got 1 return. You just flip many times, the mean return is 0.6, right? Because, that got, let me change it a little bit. If you get head, got -1, you don't gain anything, you lose 1. And what's the mean of this? 0.2, right? If I change this to 0.5, what's the mean? 0. If I change this to 0.9 and 0.1, 0.8, right? It's really simple calculation. And this is for the discrete Bernoulli case. And you can have multinomial, all these different variation of cases. It's the probability. You have to know what's the likelihood of, let me change it to -1 because I already have only -1 there. This can tell you the mean gain if that's the formulation. In this case is minus 0.1 plus 0.9 equals to 0.8. Okay, so this is the simplest Bernoulli case. However, and there's a lot of distributions are not Bernoulli. There may be Gaussian as a bell in the middle. And how do you calculate it? You have to do an integral. And let me just ask you the simplest, maybe Gaussian distribution. If my x follows a normal distribution like this, what is my mean? 0. It's actually defined by this. It's one of the most important parameters. If I change it to 2, it's 2. Yeah, I hope you actually understand this. But you have to do integral actually to get the mean. But we normally just use Gaussian. The continuous case, we normally just use Gaussian distribution, which, so you already directly know from the parameter of this distribution. Okay, so this is the expectation of the mean of a random variable. Now let's go to, if I don't just directly care, if I care some function of a random variable, which is gx. So how could I get the mean, which is super easy? You replace the same equation from the VI into GVI. Let's make a simple calculation. So assuming the t, now I care about 2t. So what is my expectation of 2t? Is it like 1.6? So my t is -1, 1, 0.1, 0.9. Now what should I do? Like here is 2t, right? It's actually 2t times, is the 2 times the -1 and times the probability of -1, right? It's 0.1. Actually, in this case, it is like 2 times 1 times, I think 0.9. I write it there. Yeah. It's just because it's exactly a scalar operation, but anyway. So what I get is 1.6. And I hope you get the idea. What is this? And you can have a function of a random variable, and then you can get the mean of that function. And for the continuous case, do the same thing. You just replace the x into gx and do the integral over all the px. So this is basic review. Now, you already know what is the expectation. We normally write it using a Greek notation mu. And the variance is, it's really just your random variable. It's a function. It's function of x. That function is x minus the mu, take quadratic. And this is variance. And after you can just use whatever you did here to calculate the variance. And I'm not going to do it, but it's totally, you can calculate what is the variance of ex minus mu for our t variable. We put it before. So variance shows how variant this random variable apart from the mean, from the expectation. Okay. And it's the same equation, but just replace the vi minus the mu quadratic into this gx function g there. It's just a specific g, if you think about it. Variance is just a specific g function. And it's about the properties of my random variable. So same thing for the continuous random variable, just a specific g function. Okay, now you understand variance and expectation. Let's start to do something. So, like I told you, random input vector x, it's input vector x. Output y, it's y. And in fact, when I'm giving a data in a supervised setting, what I'm given is x1, y1. If you remember our training data, I would always, it's that matrix. Onto xn and yn. In fact, if we want to consider, assuming what I care about the mean error across, consider all the training distributions, what I truly should consider the probability is not just x, it's not just y. It should be a joint probability, consider both x and y. So this is that probability PR, x and y. It's representing this training data. It's sampled from some distribution. This distribution is a joint distribution represented by x and y together. So let's assume there's a distribution in our data. And then let's assume we care about specific loss function. It's one kind of loss function. You actually know there are many possible kinds. In a regression, we always use MSE loss, right? The mean squared error. And then there's something called expected prediction error. So don't even worry about is this training or testing. So this is about everything. Let's consider x and y together, and your training data is just a random sample from this distribution. Your test data is also just a sampling from that data. What I cared is expectation of this loss, the y, and predicted fx. Its differences. This is the gx. If you remember, this is just the gx in the expectation formula, and taking the integral over all the possible x, y pairs. So this about expectation of the prediction error. Consider all the distributions. Consider the whole distributions. And this is called expected prediction error. And this is this is a generalization error if that's the loss that you care. So what I care is maybe L2 loss, and this is the generalization error of the L2 loss. Consider all the populations. Question about this. So this is just one example, because you can have many different kinds of L, right? For the regression, you care about mean squared error. In the classification, actually what you care is something called 0-1 loss, 0-1 error, which we're going to cover later next class. So let's just assume now we care about regression. What is the generalization of regression errors? And the expectation, consider everything. Consider all the populations. It's a very good proxy about generalization error, because it considers all the possible from this distribution. Yeah, so one way to consider generalization is to consider the joint population distribution and then consider expectation, then minimize the expectation. Minimizing the expectation of this prediction error, consider all the populations, is a good proxy about future, because I'm consider everything. Question about this. It's not just about training data. It's everything. The whole population joint distribution.
So it gives us the loss for the whole
For the whole joint distribution.
from our sample size.
Gotcha.
From our sample data.
Our sample data, it's just a sample from that distribution, right? Because whenever your training data is a finite set, right? Question about this? I'm minimizing the mean. Yeah, let's assume maybe the joint distribution is a Gaussian. The joint distribution is a Gaussian, and I'm just just making assumption. I'm minimizing the mean. So this is and most samples will have error here. I'm trying to minimizing this mean to push it to the smaller side. If my variance is fixed, which means I'm pushing, so this is the first mean maybe here, I'm pushing the mean to get smaller. This Gaussian distribution, right? I'm pushing the mean to get smaller, so this is the bigger loss. And this is smaller loss. I'm just speculating, give you simple, intuitive, but I'm a little bit abusing the ideas because this is high dimensional joint distribution, right? I'm only plotting it as a one dimensional, but I'm pushing the mean, and if I'm minimizing the expected prediction error, I'm pushing the whole distribution to be smaller. And the generalization, hopefully, because the generalization means you sample, so this is the distribution, right? You sample, so that it's possible to be here, to be there, to be here, but this consideration is the whole thing. I'm minimizing the mean, and of course, the future data will be more likely to because it's the mean pushed it to the smaller region. What I should maybe versus is this. It's another one, it's another mean. So this is the first mean, mu2, and this is the mu1. I'm pushing the mean to be smaller. Question about this? The point is, yeah, you have to have some summary of that generalization, right? Here I'm using expectation to summarize many things together. And if it follows Gaussian distribution, and you're pushing the whole distribution to be smaller. Okay, I think you get it. Okay, great. So if I'm minimizing the expectation EPE of f over the joint distribution of xy, so what is it? So assuming your true function is it's a fx plus epsilon. Epsilon is a Gaussian noise. So this is my true model. But there's always noise, right? So this epsilon is just when you observe, there's always maybe measurement error. There's a lot of this type of random noise. So what I observe on this function is how true function influenced y. And now I have a predictor function. Fx is from a training data, a specific training data. It's f hat estimated from a specific training fitting. So this is and then you can take expectation of that fx, and by averaging over the randomness of d. So let's actually just now, So there are three things we need to consider. So I'm going to simplify them as F true model, F estimated, and F bar is the mean, expectation expected. So I'm just simplify the representation here. True model, this is the truth. This is the estimated. And this is the mean of the estimated. So, question about this. There are a lot of notation in the next slide. So why don't you first memorize this. True model estimated from a specific data, training data, and the expectation of that estimated when you here this expectations over the randomness of the training data. Let's assume it's over the variations of the training data, some randomness. All right, so the expected prediction error, so now let's just do a specific sample, unspecific sample, can be decomposed. It's in fact just y minus f hat, take a quadratic term, and then expected over x1 joint distribution, right? Let's go back to see this. So what is EPE? EPEF is integral of the loss function over the joint distribution of xy, right? I did a little bit change to change it from all the possible distribution, taking the integral into just that training D, because that's what I have. And this is my empirical estimation of this expectation term. So, but here just still the same thing, y minus f hat by condition on one of the samples. So, but I want to actually make it simpler. This is a little bit complicated, so let's, because the equation there are two, I think I have a simpler version. Okay, so the expectation of f hat minus the f take quadratic. So EPE, so it's my expected error. Sorry, let's just, it's can be estimated from my current training data or variation of our training data by, and then f hat minus true f take quadratic. Yeah, so if you go back, f hat is fx, y is the true f. Yeah, there's actually a little bit. Yeah. So it's, let me actually copy the previous page. Y minus fx, and then just to make it a little easier, y minus fx. It's the e, x and y, and what I written in the previous page is y minus the fx quadratic. So, and if I remember correctly, with my derivation, yes. And then I can decompose this equivalent to y minus the true f. So this is the y, it's my observed y, right? Minus the fx and y naught f plus ef minus f hat, because this is actually f hat. Yeah, there's another level of quadratic here. Okay, question about this. So y variable minus the predicted fx take quadratic, which is the same as our previous MSE era. And I just do a reformulation by adding the true f there, true f in, and then decompose. I'm just adding a notation there, actually. Minus the f, then plus the f, and then decompose this into two summations. But on top is still a quadratic term. Okay? And then it's this equivalence to y minus the f is the epsilon Gaussian variable, right? If you look at here, you can convert it into y minus the f plus e f true f minus the f hat. Oh, quadratic. Yeah, this is right. So it takes us a little bit derivations. I have a concrete derivation in the slide, in a few slides later. You can actually just derive by yourself. So I hope this is clear. So still, this is what we care. Observed y versus the estimated fx, and take quadratic, and this is always what we care, right? In the regression case, it's the squared error. And then we just do a notation, a change of notation, by adding that true f function, true f model there. Then this decomposes into the observed y versus true f, and then this true f versus the estimated f. And this part you can actually derive it. It's the error on expectation is absolute sigma squared, which is controlled by that random noise actually in this observation. You can reduce this because just it's part of the intrinsic error. You cannot reduce it because what you observe is the true function plus some noise, and there's no way you reduce this. And this is normally called base error or irreducible error. And question about this?
So y is just f true plus some noise bias there, and bias like that we cannot control.
This is just your assumption. What you mostly, when you measure, assuming like when you measure people's height, it depends on like who is measuring that height. Just one child's height might have a lot of smaller differences, even that's just the one child. It depends on maybe the nurse who are taking this, and also the equipment taking that measurements. So this is an irreducible error. Question about this?
How do you open that whole square into two parts?
Sorry, I haven't finished this. I'm just saying the first part is this is the irreducible error. Then plus this still that part. The true f minus the estimated f, and you can further decompose, which I'm going to decompose it, but just keep that in mind for now. So this is called irreducible error or base error. Oh. Okay, so I hope this is connecting to the EPE definitions. Again, we care about estimated y versus the fx prediction, take quadratic, and then take expectation over all the distributions. And now I'm simplifying the notation by adding the true f there. So this is the part, because there's also all those random noise, like I said, because there are measurements, all those type of errors, there's no way you reduce it. And this is called base error. Now let's see the relationships. So our full error, expectation EPE error, is controlled by irreducible error and the error from the true model to my predicted model. So now we know this, right? So irreducible error, I can't do anything because it's not even relevant to my f function anymore. It's not relevant to my f function. In the end, whatever your f function is not modeling pushes to the irreducible error. Question about this?
How did you get the second step after
This step?
the next step?
Yeah, good question. There's a full slide about how you derive this, and I don't want to derive now. There's actually a full slide later to derive this. And then it's this, right? So I think I should have one more slide too. I want to derive this, just actually have all slides about every steps, but and if I derive it, it's a step-by-step derivation. So okay, so now we know it's an irreducible error and the true model versus the predicted model, right? So now this is the part. This part is actually called a risk. So E f minus f hat, take quadratic, then take expectation. I'm actually abusing the notation a little bit, but I want to simplify first, and then later, when you read the more notation, you're going to easily understand it. So now I'm just do another similar trick. F minus f bar plus f bar minus f hat. Okay, question about this. This is almost the idea, extremely important. So rather than directly, this is the true model. This is the estimated model from my current data. And I'm adding the mean of the estimated f because there's randomness in the training data, right? I'm decomposing this minus into two parts. It's how the true model differ from the mean of my estimated model, and also how my estimated model apart from the mean of the estimated model. And then you can just do a decomposition, which is actually extremely easy. Yeah, maybe let me write the other way. It's the same thing. And there's a term here. You can actually prove it's 0. So what is the term here? It's actually E 2 f minus f bar times f bar minus f hat, right? What is this? So it's E f bar minus there's a 2 here, 2 E f f hat and minus the 2 E f bar and f bar, and then plus the 2E F bar and F hat. I think I make a mistake in some minus and positive signs. FF bar is the positive rate. That's positive, and then the minus FF bar, minus FF hat is minus, then minus F bar is minus, and then F bar F hat is positive. Yes, it's correct. Okay, now E, because E F estimated equals to F bar. That's my definition because it's the mean, right? It's expectation. Then you can get what? EF hat, they totally cancel out, right? F hat, EF hat is F bar, and I think this two cancel out. This and that, and F bar and F hat, yes, actually, yes. And this part equal to 0. And what that you get is this part. Question about this? And the first part is bias, the second part is variance. Bias is how far the mean of the estimation apart from the true model. Variance is how variant is my estimated F apart from the mean of the mean. Question about this? Yeah. So this is exactly this slide's trying to show. The expected error, prediction error, is the summation of irreducible error plus the variance of the estimated F hat and the bias, the quadratic of the bias of F. And the definition of bias is, and I think I have definition. So the definition of bias is this. So this is the bias, and this is actually bias quadratic, and this is variance. All right, so there are too many equations, but I hope you understand how did expected prediction error connected to irreducible error. It really is a summation of irreducible error, variance of the estimation, and the bias quadratic of the estimation. And actually what I should condition on, this is a point estimator, so what the whole error is decomposed at a specific x position, but don't worry, if there are just too many details there. Let's understand the bigger ideas first. So now the expectation of a specific on each data point is the noise plus the bias, quadratic, and variance. And then we really know if we want to minimize expected prediction error, we should minimize bias. We should also minimize variance, right? Because that's the summation that contributes to the error. So, and this is actually all the derivations in detail, and there's actually, yes, you can look out by yourself. How do we derive this? And all the details are here. And the related reading material is also in the link I'm going to share. So you can derive step by step from the expected prediction error to the equation of this. So now you can also have another view. So rather than just see how the prediction versus the true y, you can also from another angle is from the parameter estimation. Because we always assume there's a true model, right? What do you represent the true model? the theta can be thought as a random variable too. And the whole area actually in the model parameters, it's also can be decomposed of the variance on the parameter and also the bias on the parameter. So this is in terms of parameter, there's a little bit Bayes flavor there. So if you understand about that, and so this is another view about bias and variance trade-off. This is not from the error angle, but this is from the parameter estimation angle. And this is, this is pretty advanced. Don't worry about that. So, but I think for those people who are much more advanced, you can think about bias and variance trade-off from two different perspectives. One perspective is to minimize the prediction versus the true observed y. The other is to minimize the estimated parameter versus the true parameter. All right, and the same decomposition. So again, bias in the parameter estimation angle is the same thing. How the expectation of the estimated parameter apart from the true parameter, true model. How the current estimated parameter vary from the expectation of the parameter. This is all pretty, kind of dry. Let's see the concrete equations. But so this is just using the regularized linear regression as example. If you know the true model, which is very similar to what the homework you had, you actually know the true model, right? You know the true theta, you know the true f, and we add a random noise. If you look at our generation code, we add a noise there, and that noise is irreducible noise, and because you don't model it, and then you can actually do variation. You can calculate by sampling different type of training data, and you try to estimate the performance, and then and you can actually get the bias curve, the variance curve, and the bias quadratic plus the variance curve, and the summation of the curve. And this curve, the test area, it's very good. It's kind of, because you actually cannot estimate EPE, right? Because you don't know the whole data, but the left out test area, it's quite a good proxy to, it's a very good proxy for the EPE area. And they follow the similar trend. And then everything I covered so far is just so abstract, right? So let's see, this is the best figure, I think, to understand what is variance and bias. So assuming your true theta is in the middle, is that red point. And then you're using different type of training data to estimate it. And each estimated theta hat, so each estimated theta hat is a blue point. Theta hat from the first training data, D1, theta hat from the second training data, D2, so on and so forth. You can have all the different kind of random sample of training data. For each training data, you get estimated theta. So let's just look at this figure. This is a high variance and, maybe this is a little bit difficult. Let's look at high variance and low bias case. So here, you can tell all the theta, they're quite apart from each other, right? This is more like a cloud distribution. Theta 1 is here, theta 2 is there, and all the theta kind of distributed pretty largely over the space. And however, their mean, I mean, this is a blue cloud, right? What's the mean of this blue clouds? It's very close to the center. And that center is on my true model. So this is the reason why. This is representing a low bias model. Theta hat is the mean of all those blue points. it's very close. Theta hat very close to theta truth. This is what I meant on low bias. Question about this? So it's all like because the randomness of the training data, we got this theta D1, theta D2, all the different theta D. However, their mean is almost in the center, which means the theta bar is very close to the theta truth. Question about this? However, this is a high variance model because you can tell every different theta, when there's variation of the training data, if you think about there's a Gaussian distribution or bell shape, try to put on top of all those blue points, their variance is pretty large. I mean, they vary a lot across each other. And that's what I meant, high variance is each theta d, conditional d, versus the theta bar. Blue point, each blue point is a specific training data, and then it derives a specific theta hat. Its mean, all the blue points mean is a theta bar. And the red point is the theta truth. It's the true theta. And in the end, you can think about, I'm using data to, I'm tossing the things to hit the true theta, because the randomness I'm spreading over, right? So this is the case of high bias and low variance. So every hit, all just very close to each other. No matter what du varies, they all very close, which means theta d versus the theta bar are very small. It's very small. Yeah, so this is the low variance. Low variance. However, the mean of the blue clouds is very far from that red point, which means no matter what du changes, I'm so far from the true model. And this is a high bias case. Question about this. And this is everything. If you understand this figure, you understand bias variance trade-off. All right, so I have more detail. Middle red is the truth. Blue points just from different varying the training data. So okay, so when you plot those into the curve you normally draw, so this is the model complexity, right? So in fact, you're going to have many curves, not just one curve, because there's a lot of randomness in your training data. You can actually just represent when you change the training data, what is the first data gives me the training error plot, second data training error plot, third data training error plot, and this blue curve just shows the mean. And in the test case, you can actually do the same thing too. When you have a lot of different test data, the expected test error, it's the mean curve over all the different variation of test cases. So in the end, it's really about the drawing probability of x and y, right? Whatever your sample are, they're just a sample. It's just a sample. When it's a subset of sample, there are randomness there. There are biases there. And the mean is a much better representation of everything. So even though it's a joint probability, but you normally only got a subset, there's always some biases in the subset. So the randomness, you can also, this trying to show you with the different regularization. So this trying to show when the regularization is high, your biases is pretty small. So you're changing the training data, but no matter how you change the training data, the curve are all pretty close to each other. And when your regularization is a little bit smaller, the variance becomes larger. When your regularization is extremely small, almost no regularization, so in this case it's 10 to, I think it's maybe E2. Lambda is 10 to the minus, yeah, it's maybe E, but anyway. So it's extremely super small lambda, it's almost equal to 0. So the variance is a lot larger compared to those cases. So this is large lambda, low variance, smaller lambda, bigger variance. It just gives you an intuitive way to show what do we mean bigger variance, because the curve really varies a lot when you have randomness, when you have different training data. So this trying to show the classification case, I mean, when you remove a data, and I already did this to remove a training data, and this segmentation got totally left out. But if in the k equals to 15 case, if you remove this training data, the decision boundary is most likely not going to be changed, because whenever I'm consider if a point belongs to the orange or blue, I consider 15 neighbors, not just one neighbors. So this is a much less variance model, low variance model, and this is a high variance model. It's really about the reaction to the randomness in the training data. And the same thing in the regression case, if you change a little bit and this really change the curve just varies a lot. If you change just one sample, this doesn't change much. This just show you variance is increasing with the model complexity. When you have more and more complex models, your variance actually increases. Question about this? All right. So now this is the famous variance and bias trade-off curve. So we already said, right, model complexity as when model more complex, their variance always going high, and the bias going low. The underfitted model, they have higher bias, but low variance. And here just I don't draw the variance curve. The reason why minimizing the training area, just minimizing the training area is bad is because training area keep decreasing with the model complexity. It doesn't reflect the variance at all for a specific training area. And we have to consider the variance in the formulation, so that's why you have to have a way to estimate the variance. And cross-validation, it's a very good way to have the model, the joint bias and variance. I think I already covered this. So training error can always be reduced when increasing model complexity. And expected test error and cross-validation error are good proxy for the generalization error. And the reason why we care is because we care about expected prediction error. And expected prediction error is decomposed into bias, variance, and irreducible error. And with the model complexity, variance increase, bias decrease. That's why something in the middle, because we care about the sum. I should draw a variance curve. So training and variance, and what we cared, let me draw it here. So this almost show you the bias. So bias get smaller and smaller, and the variance become larger and larger. And what we care is the summation of the two, right? That's why it got this kind of, hopefully, this kind of a valley shape. But actually, in a lot of cases, what you get, it's the valley shape in the middle, that plateau, it's very, very long. This is exactly what you observe in your homework. You observe 5, 6, 7, all give something similar in the low valley test area. It's not just really sharp, it's normally a plateau, which is a good thing. If you think about it, which is actually a good thing. If it's so sensitive to the degree, I mean, actually, it's just too sensitive to the complexity. We want to have some kind of smoothness in the complexity. Are we done? Okay, sorry, I think we're good. So, model with too few parameters are inaccurate because of the large bias, and model with too many parameters are inaccurate because of a large variance. I think that's it. Yeah, so we covered almost yeah, this is the last page. So how do you rescue? So when you have large bias, you simplify, you just make the model more complex, or you add more features, and hopefully you'll, sometimes because you haven't trained well, you train longer. And if you have overfitting, you regularize the data. You get more, you regularize the model to make the model simplified. You get more data, add more training data. So who can